define what we call minimal quasi-transitive extension of a relation, and it is defined by the relation itself, and to that we add the transitive closure of its asymmetric part. I mean, conceptually what we do is essentially the same thing as what we do with the closure, but in this case it isn't, because simply this relation is not the only way of coming up with a super relation that with a quasi-transitive relation that contains the origin. Right? So that's not, it will not work. This cannot be the closure operator, even if we assume that the relation R is Suzumura consistent. What it is though is what we call a minimal quasi-transitive extension. And what this means is the following. It only applies, it's only true if the relation is Suzumura consistent. Then this relation QE of R has the following properties. First of all, R is always contained in QE of R. It's trivial because by definition it has to be the case. So that works even without Suzumura consistency. In addition, the same is true for the asymmetric part. And that's not true without Suzumura consistency. Furthermore, R is Suzumura consistent and quasi-transitive. Again, not true without Suzumura consistency. And now we come to a minimality property that is more subtle than the minimality property of a closure operation. This relation is only minimal within the set of extensions, of quasi-transitive extensions, not within the set of all quasi-transitive relations that contain R. So basically what that means is that QE of R is contained in capital Q for all relations Q that are themselves quasi-transitive extensions of R. Again, there's a subtle difference. To be precise, for all quasi-transitive extensions Q of R. And again, you can use this example to see why this is the case. Notice that in this case, the minimal quasi-transitive extension of this relation is this. Just add the transitive closure of the original relation. But this is not minimal in any sense, in the sense of being minimal within the set of all quasi-transitive relations that contain R. Because here is an example of a relation that also contains R, that is quasi-transitive, but it's not a super relation. Okay, so that's one reason, that's one indicator that this is not a closure operator. And finally, that's actually not a property, that's a violation of the property. QE is not monotonic with respect to set inclusion. And again, here's an example. Look at this relation R. Look at the relation R prime. That's R union Yx. Well, this relation is contained in this relation. The minimal quasi-transitive extension of this relation is obtained if you add xz. This is a larger relation than this, right? This relation contains this relation, but the quasi-transitive extension of this relation is the relation itself. Okay? So that means the monotonicity with respect to set inclusion is violated as well, and again, it's another reason why this cannot be a closure operator. All right. Now I mentioned earlier the applications we have. One application we consider is in rational choice. Another topic that's dear to my heart. And I think of to rationalize the notion of rationalizability as something very fundamental, not only in social choice theory, but in economics in general. Because after all, in principle, what we can observe are what people choose. Right? We can observe someone, we can applicate, we know what their budgets are, we know what prices are. They go to the store, they buy a commodity bundle, and this is something we can observe. We cannot observe whether there is a goodness relation that generates these choices as the outcome of a maximization problem. And that's precisely what rationalizability is about. Again, that goes back to at least as far as Samuelson in the late 30s, who realized this and who provided a first analysis of what he called revealed preference. But that's essentially what it is. But his analysis was restricted to the context of consumer choice. But in the subsequent literature, this has been generalized quite substantially. For example, there is the body of work related to Arrow and Sense work on rational choice, where instead of budget sets, they allow for all possible subsets of the universal set to appear as a possible set of feasible options. That's another context in which the domain helps, in the sense that you have a lot of flexibility. You can declare anything you like, any 2, 3, 4, any number of alternatives or any subset of the universal set can serve as a feasible set, and that helps a lot. Now that the problem we are most interested in is the problem where you have a choice function without any restrictions on the domain. The domain could be anything you please. And again, that seems very realistic, especially if you look at group decisions or if you look at public decision-making problems. Typically, the bundles, the combinations of policies you have to implement or design are not don't have nice structures, right? Some of them may be continuous, like tax rates. Others may be discrete. I mean, choices whether or not you implement a public transport system, whether you have any other infrastructure projects. In general, feasible sets are not all that well behaved. And that problem the analysis of that problem was advanced quite substantially by Marcel Richter and Ben Canson in the late 60s, mid to late 60s, early 70s, and that's the model we will work. So, when we talk about a choice function, we talk about a function C with some domain sigma, that I'll say more about in a moment, that maps into the set script X, which I use to denote the set of all non-empty subsets of X, and which is such that for any feasible set S, the set of chosen objects has to be a subset of it. That's self-evident. If you want to make a choice, you cannot choose something that's not there. So script X is a set of all non-empty subsets of X, and sigma is just a non-empty subset of script X. Again, this could contain a single element. It could contain all possible subsets. It could contain, if you have enough structure on X, it could contain all the budget sets, you name it. But this is entirely general, right? Any domain we want to do whatever we do, we want to apply to any domain we might want to do. Now, the notion of rationalizability says, well, if these choices can be generated from an optimization problem that picks the best elements according to some underlying relation, and we say this choice function is rationalizable. So C is rationalizable if there exists a relation of R on the set of all possible alternatives, such that for all feasible sets in our domain sigma, what we choose is precisely the set of best elements in S according to this rationalizing relation. That is, we have C of S is equal to the set of all X in S, such that X, Y is in R for all Y in S. And of course, if your alternatives have a certain structure, like budget problems, or the consumption bundles, then you can phrase this in terms of a standard consumer structure. But that's the most general formulation, where we don't impose any restrictions on the domain. Now, an important ingredient in the analysis of rational choice is what we call the direct revealed ego, the direct revealed goodness relation corresponding to C. Call it RC. It's entirely determined by C. It corresponds to the choice function C, and it is defined as follows. So here, pair xy is in this relation RC if and only if there exists a feasible set S in our domain such that X is chosen and Y is feasible. This is, again, I think, a very intuitive definition. It works for any choice function you want to specify. An agent, a decision maker, reveals that he or she considers X to be at least as good as Y if X is chosen in a situation where Y is also feasible. In the end, Samuelson already came up with this concept. He also realized that if R turns out to be a rationalizing relation, if there is such a thing, if R rationalizes C, then it must be the case that the direct revealed goodness relation of C is contained in R. There's no other way, right? It just follows immediately from by definition. And again, this insight already goes back to Samuelson in the context of consumer choice. Now what this does is this observation gives us a very intuitive and clean and aesthetically pleasing characterization of rational choice if we don't impose any additional restrictions on the rationalization. Notice I didn't say anything here about the R having to be ordering or something. That's in the original framework, that's people required R to be in ordering as well. But conceptually, there is no need to mingle a definition of rationalizability with the properties of a rationalization. Right? Something can be rationalizable by relation that's not necessarily in ordering. Whether this relation has pleasant properties or not is